So can you see the presentation? Sorry. Can you see the presentation? Are you people there? Can you hear me? Madhura?
Yes, sir, we can see.
Okay, fine. So then let's start our today's class because I mean, where are the others? Only three, four students I can see. Hmm? So you were having like the offline classes or like what earlier before this class?
Also, we are having offline classes.
So then you must have called me on offline. No? I would have come there. Hmm?
Also, you asked me to ask everyone.
Acha.
That's why.
Chalo, anyways, it's your choice. So if I have given you the choice, then it's okay. Okay, whatever way you want to do, I don't have any issues. So okay, let's start with where we have left in the last class. So in the last class, we saw about the this NMOS fabrication steps. That what are the fabrication steps for NMOS, right? Uh, so we can fabricate the NMOS this way. But for, I mean, we will see the device, this CMOS in today's class. So in today's class, we will like mostly concentrate on our CMOS fabrication steps and then its layout and like what are the rules which we have to follow while drawing the layout. So that we will see. But before moving on to that, let's first see that what are the various device isolation techniques. So though we have grown the field oxide, which is the this which you call as FOX, the thick oxide, to isolate the devices, but there are certain problems with it. Okay, so this isolation is like first of all the biggest problem is when you do the field oxide, the thickness of the or the height of the field oxide becomes so high compared to your other structures that the device doesn't remain planar then. Okay, because of this non-planar planarity in the device, then what happens? You see, you have to like draw the wires, the interconnect wires, and the other things over this like in this thick oxides. Okay, because like you have to if you have to draw the interconnects between two devices or between two like nearby circuits or anything, then this wires should go from this wires which is called interconnects should go over this field offsets. So as this device is not planar, as the structure doesn't remain planar, because of that, what happens? The like the conductor or the interconnect which you are drawing has to face a lot of stress because it has to bend at lot many places. Okay, just because the device is not planar. Okay, it does not travel. The path will not be a straight path, sort of. Okay, in the same in the same like on the same plane. So there will be more turns when you like have this non-planarity in the structure. So because of that, the electrical stress can be there, or otherwise this mechanical stress because after like after some time there can be some cracks or something like that. Okay, into the wire. So the device reliability gets affected by this. So people want to make the devices like not the planar. Okay, they just want to remove this non-planarity. So this oxide, when you do this oxide, this thick oxide, so there is a problem because that you can like grow it over on the surface only. So rather than using that, there are other methods which people use. So I have like told you that that what is the importance of isolation. So isolation is first of all required to isolate the electrically isolate the devices. Okay, so that is what the biggest reason of isolating the devices. Otherwise, what will happen? The unwanted capacitors or the unwanted MOSFETs which will form, they will like affect the performance of the device or the circuit itself. The circuit won't work properly. So device isolation, why we need, and I also told that what is the like disadvantages of the field oxide. Okay, so I've already covered this thing. Then after this disadvantages, like what is the solution? So the solution is people go for silicon nitride, what is called as the technique which is called as the locos. So in locos we do what is called as selective oxidation rather than the global oxidation of the complete wafer or the complete device. We do the selective oxidation. Okay, so this particular locus helps in giving the this no the I mean we can get this chance to do this local oxidation. Okay, and with the help of this local oxidation, what we can do is like the selective growing of the field oxide in certain regions which where we are interested actually. Okay, not in the complete wafer, not on the complete wafer. And this silica, this the name itself suggests the local oxidation of silicon. Okay, so it is localized oxidation. So in the certain regions only. So for this local oxidation in the certain regions, what we do, we use silicon nitride rather than the oxide itself. The reason to use silicon nitride is like if you just use the oxide, then what will happen? For the later steps, it will not be able to protect this, okay, the circuit. So you will not be able to fabricate it properly. So because of that, we need silicon nitride. And this silicon nitride, what we can do is you will see later on. Okay, so it actually make the device resist. Okay, so it is helpful in making the device your planar. Okay, so this will help you to make the device planar. Okay, and the silicon nitride process, that how to grow silicon nitride itself, we have seen in the last class, that how to grow the silicon nitride. So what is the basic step, basic chemical step to grow this silicon nitride? So let's see that what happens when we grow the silicon nitride and how we use it. So here also we are not showing those steps like the photolithographic process steps involved in between, but obviously whenever there is a window is opened, so you have like this photolithography already done. Okay, only after that this window gets opened. What happened, Madhura? Oh, sorry. हाँ बोलिए बोलिए.
Yes, sir.
नो नो, क्या बोल रहे हैं आप? हाँ.
Sorry, sir, I can't hear you.
No, no, actually today there was a certain problem to these students. Okay. Okay, so they told me that they can like we can have it other day. So I told okay, okay. Particularly, you're asking for the third sem, na? This fourth semester.
Sir, I'm not able to understand.
हाँ,
Hello?
हाँ, हाँ. No, no. Actually, I mean, probably I will shift it later on. So you just in the next week probably I'll shift that class. Okay. So okay. हाँ, हाँ, हाँ. Okay, okay. Fine. Sorry, sorry. Actually, some call was there. Munmu madam was calling me, and I thought like Madhura is there. Okay, so like misinterpreted the misread it. So that's why I like called. Yeah, I thought like
Okay,
Madhura is
sir, no
calling me.
problem.
Okay, so I thought like some problem is there. Okay, okay, fine. So let's continue from where we have left. So you see, uh, what we do here is we grow the silicon nitride. Okay, so but if we just directly grow the silicon nitride over the silicon substrate, then what happens? It will create a lot of physical stress onto the substrate, and because of this physical stress, this device, like the surface, gets damaged. So to just avoid that, we first grow a thin oxide. Okay, before growing the silicon nitride layer. So that is called the pad oxide. So first the pad oxide is grown, then by this photolithographic process, the etching things, this is removed, and then the silicon nitride layer is grown. Okay, so first the pad oxide is grown, over that the silicon nitride is grown, and then you do uh, this etching process. Okay, so this is like removed. So this window is opened. Now once this window is opened, then what we do? We do the P plus doping. Why this P plus doping? This becomes important here because this actually helps you to helps to work as like channel stop implant. Okay, so it have two purpose. The oxide, the later on the oxide which will grow will get into this under this underneath this region, so it will be able to penetrate in this region. So if it is able to penetrate in this region, the height up to which it will grow later on will be less compared to what it was earlier. Okay, so we have grown this window, we have like made this window, and then we have doped it with p regions. Okay, p plus regions. Once that is doped with p region, then we like oxidize the region. So what happens, the silicon nitride wherever it was left, so it remains there, and at other places this oxide is grown. Okay. Now, this was your ped oxide which was underneath there. So this is the ped oxide which is there, and this is the oxide, the field oxide, which is now grown. Okay, in the new process. But in this process, you will see that there is like underneath this silicon nitride layer, there are two problems which we are facing. So this particular problem where this region, this P plus region is having a very this very sharp region underneath this gate, the silicon nitride or the ped oxide. So this particular problem is called your bird's beak problem. Okay, so because of this bird's beak problem, what happens? Because the two problems occurs. Actually, the oxide gets underneath this silicon nitride. So there is like encroachment underneath the silicon nitride. So that is what the first problem you face. So the active area reduces, first reason. Okay, and the second is it can give you electrical stresses as well. Okay, so because this is very like other regions, other places, your oxide is very thick, but at this particular place, it is not that much thick. So it can create some electrical stress here. So because of that, the device may get damaged. So apart from that, there are ways to overcome this bird's big problem. So to overcome this bird's big problem, what we do is we rather have certain methods which are called as silo. Okay, so sealed is the silo stands for sealed insulated oxide layer. So what we do is we this ped oxide, before growing this ped oxide, we just put a small the silicon nitride layer. Okay, a very thin silicon nitride layer, just one or two angstroms like that. Okay, so by that, what we are able to do is like this oxide. The basic problem was the oxide is getting encroached under this region, so the active area is reducing. So to overcome that, to remove that problem of bird's beak problem, or to increase the encroachment area, we seal this oxide completely. So if we seal this oxide, then there will be no possibility to grow the oxide here in this region. Apart from that, there are other methods, which other methods I just don't remember the names of those methods. But yes, the basic purpose is you make this oxide, whatever is there, in a particular in a particular like a silicon nitride layer, you grow across it also. So there is also one method which is called surface something, some name is there. Okay, so just let me see it once where it is. It's good to tell you the name of that. So that process name is your there are certain methods to do this, if I remember it correctly. Then the one method which I have told you is the sealed interface local oxidation. Okay, so the correct name is sealed interface local oxidation, SILO. The other method is your uh, mm, sidewall masked insulation. So sidewall masked insulation. So in this sidewall masked insulation, what we do, the name itself suggests the side walls. Okay, wherever this encroachment, wherever this encroachment is taking place, you enclose it in a certain. The side walls are masked with the silicon nitride. So these are your side walls of this device. So they you mask it. Okay, so that the encroachment doesn't take place under this region. So these are these are the two methods which I know. The other method is like you can use the trench isolation method also. So the trench isolation also, uh, apart from that, that trench isolation is a completely different method, but we use here also in the low cost case also we use trench isolation. Okay, so basically the idea was this active area is open. Now once this active area is opened, then what we do? this active area. Now you see, once this active area, I mean, once you get this field oxide, then by your uh, this etching process, we remove this silicon nitride as well. Okay. So once the silicon nitride is opened, I mean, this window is opened, then you have this active area window open in this region. Now, whatever process what you were doing earlier, okay, so this process, whatever you were doing, so we are at this step, let's say. So this, okay, so earlier I have shown you that this is the active area where we are going to grow the device. So rather than growing it this in this field oxide region, particularly from this field oxide, we have made a certain P region, okay, and in that P region we have grown the local oxidation. So if somebody asks you to draw the device, I mean, rather with the help of like including the locos method. So what we have to do in that case is first draw the locos method, and then when you get it this step, then when you get it this step particularly, okay, so this step, this diagram, when you get it this step, then you start showing this other steps rather. Okay, so this step, so start from here then. So then like active area is open, then you grow the thin oxide, then you grow the polysilicon, then your this polysilicon layer is like removed. Okay, the other in the other regions it is left in the gate region only, and then you make the source and the drain region. So these are the two different methods. So if you have to include the locos method in device like fabrication, then you first show those 2 3 diagrams and then continue with the remaining diagrams of what we have seen the for the polysilicon gate technology. Right. Mm. So this was about the locos method. So why we use locos method? It is just to make the device more planar. So that was the reason to do it. Okay. And in the locos method, we use silicon nitride. Second point. Third point, I mean, there is a problem of bird's big problem. There is another problem which is called the bird's crest problem. So in the bird's crest problem, what happens? This surface gets more uh, get uh, mm, little raised up. So that surface here near this region gets little raised up. So that is also like can be removed later on in the steps. So that's what you have to see. So bird's big problems and the bird's crest problem. There are two problems which arises in these locos. So to remove these problems, we use what is called as silo, and the other one is sealed this isolation trench isolation methods. Okay. So sidewall masked isolation I have told you. So these are the two methods which we use to overcome this bird's big problem. Once this is done, then we follow the same process what we have done for our NMOS fabrication with polysilicon technology. Okay, polygate technology. So now with this, let's move on to the CMOS process flow. So in the CMOS process flow is again same, more or less, but here we will do like you see, our base will be our substrate will be of one type. Let's say it is of P type. So then we have to this P devices cannot be grown up cannot be made in a P substrate. So what we do, we make it a certain region where we do uh, this end doping. So that is called the well region. So N well. Okay, so we form certain region, certain isolated region on that substrate, and we then later on make all our end devices in that region. If it is a P substrate, if it is opposite, if it is an N substrate, then we make a P region separately, which is also called the tub or the well. Okay, so it is the tub which we form there, and then all the type, I mean, all the one type of devices. If it is an N tub, then we make all the P devices in the N tub, and if it is a P tub, then we make all the N devices there, depending upon what we require. So the basic steps will be more or less same what we have done earlier, but we have to form a tub here. So this is what uh, the change which you will see from the previous process. So you take a substrate, then you form a tub, then you make the isolation regions, and then you form the channel doping implant. So channel doping implant is done, then the gate oxidation is done, then gate electrodes metallization is done. Okay, so gate electrode formation, and then the source drain formation, and then finally the metallization. Okay, so these are the steps which we do here. Acha. This particular channel doping is important. Okay. So channel doping is not required in case of your the PMOS devices, but whenever you have to make an NMOS device, the channel implant is required because of this fixed charges, fixed trapped charges, which are there in the this oxide layer, and the nature of those fixed charges is always positive. So because of that, what will happen, your threshold voltage will become negative. So that is why in case whenever you have to make an NMOS device, you always require a channel implant or the channel doping, okay, to make the device, the threshold voltage of the device positive. Okay, so this was it. So the typical your CMOS fabrication steps so first we will see this N-well process. So earlier it was P-well process which people used. I mean, I'll show you that as well in one of the diagram. But what we will see here is your N-well step, this N-well fabrication. So the 15 steps we are going to see here. So the 15 diagrams I'm going to show you. So let's see them one by one. Okay, and you will understand it like what we have to do. So first of all, this photoresist coating and all those things we do, and we open a window. And the first thing is annual implant. So this implant gives you this particular region here underneath this surface. So in the P substrate, if the substrate is of P type, then you make the annual region here. So the well region is formed. Now all our devices will be formed in this region only. Okay, and now you see what we have to do is we are using now, let's say, low-cost method to fabricate the CMOS. So in the low-cost method you are using actually the silicon nitride. So first a pad oxide, a thin pad oxide layer is grown, then over that a silicon nitride is grown. Okay, so after that again you make the implant, and like this is your what, channel stop implant. So in the channel stop implant, what we have to do is we this channel stop implant, this again you expose it to that particular region, that layer. So after like photolithography and etching out, this particular windows are opened, so you expose it to the this N implant, okay, this N type field. So then what happens, this N type material will circulate your regions, this this well region. So what will happen, your this active region will be like you are actually defining the active region in this case. Okay, so you have to define the active region for both the anvil region, anvil area, and the PVL region. Why I am calling it active region? Because you see, when you will see the layouts, you will see that the device cannot be very close to this boundaries of the well. Okay, they should be like sufficient apart from that to demarcate the difference between the two regions. So you need a certain separation between the boundary and the device which is closest to this boundary. So for that we actually like restrict the devices to be fabricated in a certain region in this anvil region. So we have to make an active area. So that active area is basically defined by this end field. Okay, so that is what I'm saying. So this active area is defined by this. So once that is defined, then you define the active region for the P region also. So now this particular you have like covered anvil with the help of photoresist, because you are using implant. So photoresist can act here, can act as your this cover. Okay, so you have covered this complete thing. Okay, by this process, and then later this is exposed. So now the P layer, this P active region is formed here. So once that regions are formed, then you have like one this field oxide is grown. So isolation. Okay, so local oxidation you have done. So field oxide you have grown. So with the help of locos, as I have already told you, we have like made these regions. So this field oxide is grown here. Now once this field oxide is grown, now we cover the surface, the whole surface with the polysilicon. Now this polysilicon will later on be removed, and it will be left in certain regions where we want actually our gate to be like the place where the gate will come. So it is removed now in this place. Okay, and this is like you see, yes, this particular terminology which I was forgetting there. So you see, to protect this region polysilicon, we use this SiO2 spacer as well. Okay, so this actually your silicon nitride was there earlier. If you just see, So you see a silicon nitride layer is still okay. So that silicon nitride layer was there, then you have removed it, and then underneath this is polysilicon. So but underneath that polysilicon there is a small layer as well here. Okay, so a little thick line which you can see here. Okay, so that is your actually this gate region you will form here. So a gate region is also okay. The gate oxide is also there. So gate oxide and the polysilicon is over there. Apart from that, just to like just to cover that this encroachment should not happen too much into this region. So you put this SiO2 spacer. So that is what the reason is, to put this SiO2 spacer here. So SiO2 spacer lets you to like if there will be certain encroachment, so you can like more finely control that encroachment. Okay, if it goes underneath I mean somewhat under this region as well, so then your device will be your like gate will be more defined. Okay, its feature size, its feature dimensions will be more defined in case of this case. So SiO2 spaces we let it remain here in this case. So then later on, after this process is done, we do again the source and drain region implants. So in this source and drain region implants, this all the windows are opened. So this particular window is open for your P in the P substrate region, and we will form this N and source this N and source and drain region for your NMOS device into the P substrate. Okay, so this is what we are forming, and then later on again the same step is repeated for your P devices. So where is that step? Eight, probably some. Actually here it should be like P-type substrate. Okay, P-type source and drain region. So like I have like done some mistake while making this. So this is like what we are doing is rather than an implant, this particular thing is now covered. Okay, this particular NMOS is now covered, and we open a window here. And then if this window is opened, then you actually make the P-type devices here. Okay, so P-type device, for the P-type device, we have to grow the source and drain regions in this region. Okay, so source and drain region is formed in this region. So once that is formed, then you have this structure. So this structure is actually giving you this, this is your NMOS and this is your PMOS. Okay, so you form these two regions. Now once this is formed, then we do this this contact formation and your protection of the device. So two things are still remaining. So first we cover this there's no I mean after channel implant, first we have to do the annealing. So after annealing what happens, the source and the drain regions get little more deeper into the this substrate. Okay, so earlier they were little near the surface, and then later once that is done, then it gets little deeper into the surface. Okay, because of this annealing, because you are increasing the temperature, so the materials get diffused inside. After that, you protect it with this borophosphate phosphosilicate glass. So actually, you coat this material with like now you grow the you make this deposit this layer over this just to protect the other regions where you don't want the charges to get affect this device, because later on at the other when you will do the further processing, when you will make the metal contacts and the multiple layers of the contacts, then this device may get like interference, or their signals may get interfered because of this thing, or they can get mechanical stress as well. So to avoid that, we encapsulate first of all it, I mean not complete encapsulation. It's not the outside encapsulation which you will see, it is just the local encapsulation which you are doing here. Okay, and local encapsulation, or you can say like whatever at this level encapsulation is required, you are like protecting this device. So this layer is actually a non-conducting layer, an insulator layer, and it protects the device. Okay, so this is what you are doing here. Once that is done, then you again open a window to form the metal contacts. So then the metal contacts, the aluminum contacts are formed for the source and drain regions. And then once that is done, then you completely encapsulate the device. Okay, then what is called as the passivation. So then the next step is your passivation. So after metal contacts are formed, then the next step is your passivation. So here actually the multiple layers of metals are shown. So first you have formed this first layer, and then over that, if you want the other metals, which like metal layers, which will connect various different modules in the on the circuit. Okay, so to connect the various different modules, you require long connecting wires or the long interconnects. So rather than growing them at the same plane, we grow them at the a little higher plane. The reason is, in this case the interference will be less, because if they are at the same plane, then there will be more interference because the isolations will be less in between the interconnects. So what we do is we make a insulating layer, and over that we grow that long wires, because that long interconnect wires will run throughout the chip. Okay, so they will not be localized, but they will run throughout the chips. So just to like protect the device from the interference, we grow these metal layers little above. Okay, so and like this particular metal layers, if have to be connected somewhere to the device, then they are connected with this what are called as vias. Okay, so these are vias which are like holes drawn into this insulator layer, and from that the wires are connected to the other wires. Okay, at the other layer. So after that, the final step is the passivation. So then once that complete device is fabricated, then you encapsulate into a casing. Okay, so then the passivation is done, and now the device is completely protected from the atmospheric conditions. So if there is like humidity, then also the device should be protected. So this passivation layer helps in protecting the device completely. So this is what you do, and so this was the process for your CMOS fabrication. So any doubt so far in this? Any doubts?
So can you
Passivation
explain
is actually
passivation?
your growth of oxide. Okay, but what you see, I mean, passivation is like growth of oxide, but at not that high temperature. It's at little less temperature. So what happened? Your it is sort of glass. So you see, SiO2 is nothing but the glass. So passivation, when I say, it looks like a complete SiO2 layer. Okay, so that is what it is. Passivation. You call it passivation because you are using it to protect it from the device from the atmospheric conditions. Okay, humidity, the temperature. So suddenly the temperature will not also change. Okay, so that is what they think is passivation is, right? You use the same method which you use for oxidation to do the passivation, right? Okay, so rather than growing the oxide,
Okay,
as
sir.
there is no silicon dioxide, what we do, we deposit the layer of silicon dioxide. So that is what we call the passivation.
And sir, what is this
Are
FOX and
FOX, you tell me,
BPSG?
what is the FOX? This is called field oxide. Okay, field oxide. Field oxide is for your what? Isolation between these two devices. Okay, these nearby devices. So
Okay, sir, I was confused.
this is also called
And sir, what
this field oxide
BPSG?
is also called your thick oxide. Okay, this BPSG is like, see this in this layer we have grown this BPSG. It is borophosphosilicate glass. Okay,
No,
so what is actually what
silicate class.
this
Okay, sir.
this layer is doing? It is also protecting this device. Okay, this particular single device. Whereas the passivation layer is now protecting not only this device but these metal layers as well. Okay, the complete circuit. Okay, so that is what the difference is.
Okay,
Clear?
sir.
Okay. So this was about the
Yes, sir.
N-well process. Now in the P-well process, again the steps will be same, all these steps, but rather than making the N-well, we make a P-well. Okay. So in the very first step, when you have made the N-well, rather than making the N-well, we make a P-well. And earlier you have taken a P-type substrate. Here you take a N-type substrate. So that is what the difference is. Okay. Otherwise, the steps will be same. The same way, the way by which you have you have made the N-well, the same way you will make the P well. Okay, so this is P well process. Then the another process is twin tub process. So in the twin tub process, we make two different tubs, one for holding the N devices, the other for making the P devices. So the place where we will make N devices, we will make it P well, okay, that particular region. And the devices where we are going to make PMOSs, that region will be called as the N well. So now, rather than making the single well on the substrate, you make two wells. And along with that, we also grow a epitaxial layer. Why this epitaxial layer? That we will see later on. So the epitaxial layer is like made by this physical vapor deposition or the chemical vapor deposition, depending upon depending upon what quality layer you want. Okay, so the epitaxial layer also plays an important role in like protecting the device from what is called as the latch up problem. So that we will see after completing this all discussion, because that is like a little electrical discussion. This is all like theoretical things, but that is like little electrical thing which we have to understand. It will actually happen at the circuit level. So a circuit is involved actually there. So that we will see later. Okay, so this is called twin tub process. So once you have formed two separate regions, two tubs in which you will form the anvil and the p-well regions, then other steps are same. Okay, so anvil formation, p-well formation, so again you have to follow the same steps. Okay, so this is called twin tub process. Now after this, so this was all about your device fabrications, NMOS, CMOS. Okay, so that's what we have seen in general. So from last 2 3 classes, so whatever like introductory things we were doing, so these all things are used in this particular fabrication. So this CMOS fabrication and the NMOS, the CMOS fabrication is more important for us, and that CMOS fabrication we have done for our N-well case, then the P-well case we have seen, and then the twin tub case. Okay, so no need to show all these steps for twin tub. Again, these steps will be same. The only thing is you have to form two wells. Is it clear so far? Is it clear? Clear now? It's a theoretical things.
Yes,
Now
sir.
let's see. See, this all thing you have to like masks and all those things you have to do is for that you have to actually draw some drawings. So those drawings are are called layouts. Okay, so layout whenever I say, so it is nothing but the drawings. Either you make it manually or you automatize it. See, I mean, when the circuits are very small or when you have to do it for single devices, then you can do it manually. But when it is like a large circuit which holds millions of transistors, it is like nearly impossible. Okay, it's impossible to make that manually. So what we do, there are some the softwares in which there is automation. This layout process is automatized. So to do this, like automatically when you put these numbers, so it will make this layout for you. But this layout, if you are making, then there should be some rules which you have to follow. Otherwise, what will happen? See, in the earlier steps, when you have seen that this particular region should be there, and in this region also, there is some region which you define the active region, then the source and the drain region. So everything is like very small, okay, very miniaturized. So these things you have to, and like they should be isolated from each other, and we should be able to separate that which line is p, which line is n region, okay, where is your polysilicon. If you are not able to differentiate between them, then there will be more of there, I mean, not only you should be able to differentiate, but the the electrons which are flowing in those metals and this particular devices, they should be able to separate them. So this electron, so we need very specific like rules to make this drawings. Okay, so these rules which are like there to make these drawings are called the layout design rules. Okay, so these layout design rules are basically defined in two ways. So one are called the micron based rules and the other one are called the lambda based rules. The difference between them is it's like just the difference of unit. So in the micron based rules, what we do is like all the dimensions of the drawing, we define in microns. Okay, but in case of lambda based rules, we define all the dimensions with respect to our minimum feature size or the minimum dimension which we can draw on that layout. Okay, so let's suppose if you can draw the minimum dimension of 1 micrometer, so then your lambda will become let's say 2. Okay, so twice of the minimum dimension, let's say that will become lambda. So you know that, let's say you want to make a, and why these lambda based rules are more useful, because if you are moving from one feature size to the another feature size, earlier you had like 1 micrometer devices and now you want to make 0.5 micrometer devices. So then all the micron based rules you have to remember, you have to completely remember the new rules, or whenever you have to draw you have to remember that this now the things are like should be reduced by this much number. Okay, and you have to do the all find the these numbers in the micrometer and then draw the drawing. Okay, then you have to draw the things. But if you use the lambda based rules, then it is very easy to like draw the things when you are scaling up or scaling down. So when let's say you are moving from one feature size to the another feature size, and now you if you once you find that what is the ratio between the earlier feature size and the new feature size, then you can just change all the rules or all the dimensions by that factor, right? If suppose first you are using 1 micrometer, so now and that 1 micrometer was like let's say defined by 2 lambda, and now if you are making it 0.5 lambda, this 0.5, so you will say that the next stage is like the lambda in the next stage is 0.5 micrometer, so no need to change it. Again the dimensions you have to keep the same, so you can like again say that it is 2 lambda, the gate length is 2 lambda, right? Because the lambda itself you have changed. So if you just change lambda, the I mean you just define the lambda once, then all the rules will be accordingly automatically get reduced. Okay, all the I mean not rules, all the feature size, all the dimensions will get automatically reduced. Okay, so rather than drawing the complete drawing again with the help of micron rules, if you make dependent it on certain factor which is lambda, so once if you just change the value of lambda, all the sort of dimensions will accordingly get reduced. So it is just a sort of formula which you use in Excel. So if you are using a formula in the Excel sheet, then what will happen? We just substitute that value, just change the cell value, and then all the cells where you are using that particular formula, that particular cell value will get automatically updated. So that is this particular lambda is how much, I mean how it is useful. So that's what the elaboration was about. So once you have this lambda based rules, then this is a little difficult to see, I know, but still I will just show you one or two slides based on this so that you know that uh, how the drawing looks like. Okay, the purpose is just to show you this. Can you see it more clearly now, or should I magnify it a little bit more? See, let me try. So you see, let's say this is your anvil region. Okay, so this anvil region, what you have is this anvil region. I mean, all the dimensions, there are certain rules that the minimum width of the anvil region cannot be less than 10 lambda. Okay, minimum spacing between these two cannot be less than 9 lambda. Okay, so you see, these are the rules which you have to remember. There is nothing, no engineering is involved in this. The only engineering which was involved while defining these rules, okay, that like how much minimum distance the device will be required to isolate them, okay, to not have the interference between them. So that all engineering, that all calculations was done earlier. And once that things were done by the fabrication laboratories, then they give these rules to you. So whenever you are people are drawing the layout, whenever they are drawing the forming the drawings for these circuits, they have to just obey these rules. Okay, for a particular fab lab. So whenever like you are you want to design a circuit, so that you know, okay, from the beginning that which to the which fab lab you are going to send this design for fabrication. So you follow the rules of that fab lab. Okay, and if there is a change at the later stage, then obviously you have to make the new drawings. Okay, so depending upon the fab labs, they whatever type of machines they have, okay, the precision type of they can offer, so they gives you these rules. So whenever we have to make the circuits, so this is like we have to do. And I'm not going to show you all these rules, but you should know that what is the actually what I mean at the layout step, what actually happens and what you have to do. Okay, and these layout designers are also like paid very heavily, okay, in the industry, because though it is automated, but still people have to like do the manually things, and where and those manual things which engineers need to do is very like precise, and it needs I mean too much sophistication. Okay, engineering skills it requires, so that is why they are paid so heavily. Mhm. Is the slide changing? Can you see the layout rules of minimum size MOSFET? Hmm?
Yes, sir.
No, no. Is the slide changing?
Yes, the layout design with
I'm changing the slide. So can you see it? Or it is same? Changing or huh? It's not changing.
no, sir. No, sir. So if you are changing the slides, it's
Now is
not
it?
visible.
Earlier also you were. Okay.
Yes,
Now
sir,
it
that
is. You can
layout
see it.
rules of a
Okay.
minimum size
So you see,
MOSFET.
when you are like just showing the rules for a at a for a single device, then you have to see this many things. Okay. At the single device level, I'm just showing you the rules. So you see, this is the polysilicon width. So the minimum width of the polysilicon which you have to keep. So that is what is required minimum. And over that, you have to like keep this dimension as well. Okay, the vertical dimension. That how much it can go, how much minimum it should extend. Okay, you can extend it beyond that, but minimum that much extension over this active region should be provided. So let's say if you're just making a device, okay, a single device, and it is asked that what is the dimension of the device. So then what you have to do is you have to calculate that like in a particular feature technology, in a particular technology in which the minimum feature size is already given. So you have to see that what is the minimum polysilicon layer which you can grow. So this will become your gate length. Okay. So whatever this dimension is given in the problem, so that will become your gate length. Okay, then the distance between the source and the drain. Okay, so that is actually where you will have this devices, isn't it? So you see, accordingly you can find it. Okay, so this is the contact window which is formed here. So where the contact window will be formed, what will be the separation between this? Okay, what is the this active area which is required? Hmm? So this is the source region where you will form. This is the drain region which you will form. So if you want to find, like say, want to calculate the various parameters like the capacitor. Okay, so in the capacitor you need the area of the device. So this particular dimensions will help you to find that area of the source and the drain region, the device dimension, the length of the gate. Okay, so you have to just see these rules once. Hmm? So these rules, we will come back to these rules, but not, with very precise dimensions. We will draw the rough diagrams for this. These rough diagrams to show these layouts are called the stick diagrams. So these stick diagrams, we will later on, we will see that this will come back to this layout particularly in the form of stick diagrams in our last unit. So till the last unit, like this is like postponed. Okay, I've just shown you that how the layout will look like, right? But we will see this at the end of the like the course. Okay, once again we will revisit it and we'll see that how the layouts are drawn at the roughly they are drawn, and then how to use it to design the things. Okay, and I mean, so that's what they think is. So with this, let us finish our today's class. In the tomorrow's class, I think tomorrow's class will be a little shorter, and we will complete this the remaining things, right? So not much is remaining, but today's time is almost over and we will not be able to complete it in 5 minutes. So let's complete it in tomorrow's class, and then we will start with the new unit. Okay, is it okay? So any doubts? If you have any doubts, you can ask me. Hmm? Any doubts so far? Or we can go for the attendance.